Hey guys, so on the bench today we have automatic water change systems for saltwater tanks. So I'm planning on doing a few videos on automatic water change systems. I'm hoping that this can be a good reference for people who are interested in setting up automatic water changes, but they're a little bit confused by all the different options out there and they're not sure what will work best for their tank. So I'll make an overview video at the end. But the three types of systems that I have seen rely on either a dual head peristaltic pump, float switches in the sump, or external reservoirs. And there's a lot of variations on these types, but the concepts are all the same, and even two of the methods that I just listed are basically the same. They're just a variation of where the water exchange takes place. So today we're going to start out with the dual head peristaltic pump method, and that's what I have here. It's two peristaltic pump heads on a motor. And what we're going to be doing is using the two peristaltic pumps, one pump head to pump wastewater out of the sump and to a drain, and the other to pump fresh water into the sump. So here I have a representation of the two heads, and on one side of the pump head the water moves in one direction, and on the other side it moves the same direction. So we just take one of those inlines and we connect that to our sump, and we put that same line to the drain. And then I take another one of the inlines and I take that to our fresh salt water reservoir, and I put that one to the sump. So we can see that we should have equal amounts of water coming from the sump and going to the drain, and water coming from the fresh salt water reservoir and going to the sump. Now that's the general idea, but what are some of the benefits of a system like this? Well, for starters, these systems are very simple. We just have two lines. They're also very reliable, provided that you have a good quality pump. They're also compact. These pumps can fit nearly everywhere, and the system as a whole doesn't take up much space. They're fairly low maintenance. There's not really much to clean or upkeep on them, and because of their size, they kind of require more continuous water changes, which results in greater stability. On the downside, these pumps are somewhat expensive. They can be found fairly cheap on eBay, but they typically are around $100 or greater. You have to replace the tubing, which is most frequently silicone tubing, on a regular basis. I don't currently run this type of system for this purpose, but I do run a similar system for another purpose, and I replace my tubing at least every year. Depending on the size of the dosing pump and the pump heads, you have a somewhat limited water change volume. Although in reality, if you were to run this continuously, you could change way more water than you would ever need to change. These pumps are often noisy. So that's what this pump sounds like. And it's not the quietest thing on earth. If it was in your basement, it definitely wouldn't be a problem. But if it's in your living room, it might be a little bit too loud. They're typically industrial or laboratory pumps, and therefore they aren't really designed to be quiet. But those are all minor concerns. The two big concerns are, well, one big concern is that there's often error in between the pump heads. So that means that one pump head, for whatever reason, will pump slightly more or less than the other. And the other concern is that the more frequent we make our water changes, the less efficient those water changes are. Alright, so let's look at those last two problems a little bit further. So we'll start with why smaller, more frequent water changes are less efficient. Now, a more frequent water change provides greater stability to your tanks, but it is slightly less efficient at changing the water in your tank. So we need to strike a balance between that frequency and amount. So I put a link in the build thread with to a great calculator with an effective water change volume calculator. But here's the basic idea. Let's say that we start with a tank that is full of water. And if we do a 100-gallon water change, meaning that we change all 100 gallons, then we've done a 100% water change. But if you change 100 gallons and you do it in 2 batches, meaning that you change 50% each time, let's see what that does. So the first time I'm going to change 50% of the water. Yeah, 50% of the water. So I've done a 50% water change. Now if I again change 50% of the water, so that's how much water I changed the first time, and I'm now going to change another 50%. That's how much water I've changed the second time. Now you can see that both times I split the tank evenly, took out half the water. But here we have 25% of the water left that has not been changed. So we've effectively changed 75% of the water by changing 100 gallons. So we've lost a 25% efficiency when changing the water this way. Now this might sound really bad, but this is kind of a worst case scenario because we're trying to get to 100%. But let's use a more realistic example. Let's say that we want to change 15% of the water every 2 weeks in a 100-gallon tank. Well, if we want to do that, we could change 15 gallons every other week, and we would get a 15% water change. Now, we could also change the same amount, but space it out to every other week, and we would get a 14.5% roughly water change. So not 15%. And if we did it every day, we would get about 14% of a water change. And if we did it every hour, we'd get about 13.75%, and every minute, or basically a continuous water change, you get 13.5%. So it's asymptotic down to that 13.5%. So we get an initial penalty, and that penalty decreases as we change more and more frequently. So this isn't really that big a problem. We just have to account for this, and we have to budget a little bit more money for salt, and we have to change a little bit more water. But as long as we're accounting for it, it's not that big a problem. Alright, so the second more important concern is the error between the two heads. So I'm going to use this setup that I have to the side here. Let's zoom out on that. So I have a 1,000 milliliter graduated cylinder here, and a reserve tank of water here. I've got my dual head Peristaltic dosing pump here, and 2 heads. And I'm going to be using that as an example. So I did a couple tests on this system. I ran it for 30 minutes, and over the course of 30 minutes, the water going into the graduated cylinder, which I'm using as my sump, was 250 milliliters less than the water that went out. So we have a 250 milliliter error between the 2 pump heads. So that was over the course of 30 minutes. Now, to find out how much water was changed over the course of 30 minutes, I timed how long it took to fill up a 1,000 milliliter graduated cylinder, and that took 4.5 minutes, which means over the course of 30 minutes I changed 6,666 milliliters. And we can figure that out just by taking 100 or 1,000 milliliters, and it took 4.5 minutes to figure that out, and that is equated to our unknown amount of water that we pumped and the amount of time it took us to pump that water. Then we simply cross multiply, and we get 1,000 times 300, so 30,000, or 1,000 times 30 is equal to 4.5 times x, and then we solve for x. And we get this 6,666. So that's how much water was pumped, and we had an error of 250 milliliters. So if we take 250 milliliters and we divide it by 6,666 milliliters, we get an error of 3.7%. And that's the error of the pumping between the two pump heads. Now that might sound like a big problem, but it's actually pretty easily fixed. So a lot of reef keepers shoot for 1.026 SG, or 35 parts per thousand. So that 35 parts per thousand means that for every 1,000 units of water you have 35 parts of salt in that water, or 3.5% salt. So to solve our two pump error problem, since we are pumping in this case 250 milliliters less water than we are pumping out, we can pump in a more concentrated salt solution and let the ATO make up the rest. Now if we were doing the opposite, we were pumping in 250 milliliters too much, we would just do the opposite. We would pump in a less concentrated salt solution and let evaporation make up the rest, essentially. So we have this 3.7% error. If we multiply our desired concentration, or 35 ppt, by 103.7%, or 1.037, then we get the needed concentration of our fresh salt water, which in this case would be 36.295 ppt, or 1.0274 SG, or specific gravity. And I'll put a link down below where you can find the calculator that you can translate different measurements of salinity between each other. So if we pump in water that is at 36.295 parts per trillion, then for this setup, it doesn't matter that one pump head is pumping more than the other. Everything will equal out because our ATO is going to pump in a little bit more fresh water, which will dilute this more concentrated salt water to get it to 35 parts per thousand. So there are a lot of these two-head pumps out there, but the most common type uses Cole-Palmer pump heads connected to a motor block, and that's what I have here. I have two of these Cole-Palmer pump heads connected to a motor block, and this is an Amicon pump head, but you can also get them in all other sorts of configurations. This is a Masterflex, which is a good brand, which is pretty popular and also makes the pump heads. Now these pump heads are stackable and interchangeable, meaning that you can buy one of these pumps with just one pump head, and then you can add another pump head onto it like that, and you just bolt them together, and they then work in concert. So that's what I've done here, and you'll see that if I turn this on, then I'm going to pretend that this is the reservoir of fresh salt water, and I have my waistline going back into the reservoir just so I don't have to set something up. But there's water being pumped out of this reservoir of fresh salt water, and it's being pumped in to my sump, which I'm using this graduated cylinder for my sump. And it's then being pumped out of my sump by this line. And that would go to waste, or in this case, to my reservoir. So this pump is pumping the same amount of water into my sump as it is out of my sump. And we can figure out how many milliliters per hour this pumps, and then we can figure out how many minutes to turn this on for per day and at various times a day, depending on how much water you want to change. So these pump heads also come in different sizes. Here I have a fairly standard size. It's a 7016 by 20, but they also come in larger sizes and smaller sizes, so you can fit the size of the pump head to the amount of volume that you want to pump. And I'll put a link down below in the description to a list of the different pump heads and their pumping volumes. So these pumps themselves are pretty expensive, but they can be found secondhand on eBay for usually around $100, sometimes a little bit cheaper. And even though these are secondhand pumps, these are built to run continuously. So they're going to last a really long time, as long as you keep it, the motor out of a saltwater environment. So keep it isolated from your saltwater system. So there are other options to this pump out there. You can even find a really small two-head Chinese pump for $30 on eBay. I know that these are not continuous duty rated motors, and I don't know how long they're going to last, but they are $30. And maybe for a very small setup, they'd be ideal. So a variation of these dual head pumps are the multi-channel peristaltic pumps. And these have a single head, but they can accept multiple lines within that single head. So you can see this one. And these often have more rollers, so they may be slightly more accurate. However, they're not going to usually be quite as bulletproof as these Cole-Palmer pumps. These Cole-Palmer pumps are really meant for industrial applications, and they're meant to be practically indestructible. These multi-channel pumps are usually designed either for the medical or science fields, so they have a little bit, they have people checking up on them more frequently, so it's not as important that they run in really dirty, awful environments like our saltwater tanks. So another option to using dual head pumps or the multi-channel pumps is to use two separate calibrated dosing pumps, like a liter meter, the dose pumps from Neptune, or any of the programmable 3 or 4 head dosing pumps like the Jabo, Bubble Magnus, or GHL. So the higher quality the pump and the motor, the better that this will work. I use 2 of the Jabo 4-head dosing pumps. I really like the pumps, but they drift pretty significantly over time, and they require some amount of correction. So those may not be the best candidate for this setup. So the benefit to using multiple programmable heads is that if we have any difference between the 2 heads, we can correct for that, meaning that we don't have to mix our salt to a different value. The downside to this is that the errors between the 2 pumps will generally be greater, and we will see drift between the 2 pumps, meaning that the amount the pumps pump will change between each other over time. There's also a greater chance that a motor or pump head will fail, and this will cause the pump to pump little or no water. So basically we can achieve greater accuracy with multi-motor setups, but it comes at the cost of maintenance in the form of calibrating the dosing pumps and a little bit of safety and reliability. Alright, so that's it for water changes with dual head peristaltic pumps. So this is a great option for those who have limited sump space, would like a more continuous water change, and those looking for reliability. On the downside, we have to watch out for salinity drift due to differences between the two pump heads. As always, thanks for watching, and if you have any suggestions or DIY ideas, please put them in the comments down below.